Let's test the famous strawberry problem. It's a running joke in the tech world that super smart AI can pass the bar exam, write flawless code, and summarize entire books in seconds, but it fails completely when you ask it to count the number of R's in the word strawberry. When it hallucinates the answer as 2, people often laugh and assume the AI is just dumb. But it's not a reasoning flaw at all, it's a reading flaw. ChatGPT fundamentally does not see letters. It cannot read English. It reads numbers. Today, we are going to uncover exactly what a token is, why it breaks the AI's ability to spell and do basic math, and how it secretly taxes foreign languages. It's the full story of the invisible filter that sits between you and your AI. When you type a prompt into a chat box, the model doesn't ingest the English text directly. Computers, deep down, only understand numbers. So, your text is aggressively chopped up into little pieces called tokens, and each piece is assigned a unique ID number. Imagine reading a book where every concept is replaced by a unique barcode. If the model doesn't have a specific barcode for the letter R, it literally cannot see the letter isolated from the rest of the word. A token can be a whole word, a syllable, or just a single space. When you type "Hello World," the AI might see the numbers 15.96 followed by 9.5. Tokens are the native alphabet of artificial intelligence. It doesn't process text, it processes mathematical representations of text. If we have to map text to numbers, how should we chop it up? The most obvious, naive idea is character-level tokenization. In this system, one letter equals one token. The letter A is 1, B is 2, and so on. The main advantage here is that the dictionary is just 26 English letters, some numbers, and punctuation. But there is a massive downside: it takes way too long for the AI to read. Imagine trying to read a thick novel, but you have to sound out every single letter, one by one. The AI's working memory, known as its context window, would fill up almost instantly. The system would become painfully slow to generate text and highly forgetful over long conversations. So, characters alone just aren't efficient enough. So, let's swing to the exact opposite extreme: word-level tokens. What if every entire word gets its own unique token ID? Cat is one number, catastrophe is another completely different number. This approach fixes the speed problem perfectly. Sequences become very short and lightning fast to process. But it introduces a fatal flaw: the dictionary size absolutely explodes. The English language has hundreds of thousands of words. Once you add in character names, typos, internet slang, and computer code, you're looking at millions of unique ID. The AI's brain would require a colossal, highly inefficient memory bank just to store its vocabulary list before it even starts learning how to talk. We need a way to keep sequences reasonably short without memorizing millions of unique words. What we desperately need is a Goldilocks solution. Not too granular like individual characters, and not too massive like whole words. Enter Subword Tokenization. Instead of entire words, we break language down into common chunks or syllables. The word unbelievable doesn't get a single massive token, nor is it split into 12 single letters. Instead, it becomes a few common chunks: un, believe, and able. Extremely common words like the or apple might stay completely whole as single tokens. But rare words or typos get broken down into smaller, recognizable pieces. This brilliantly balances the dictionary size with processing speed. It is the secret sauce and the fundamental compromise behind every major large language model operating today. How does an AI figure out what these chunks should be? It uses an elegant algorithm called byte pair encoding, or BPE. Before the AI even learns to speak, it runs BPE over millions of books and articles. It starts by looking at raw single characters. Then, it scans the text to find the most frequent pair of characters, for example, T and H. It merges them into a brand new token, TH. Next, it might find that TH and E appear together constantly, so it merges them into the. It repeats this exact merging process thousands of times, building up a vocabulary of the absolute most useful text chunks based entirely on statistics. The chunks that appear most often get their own dedicated tokens. Because BPE is purely statistical, the final dictionary depends entirely on the books and websites it was trained on. This means not all AI models use the same token dictionary. OpenAI developed a proprietary tokenization system called TikToken for the GPT family. Google, on the other hand, often relies on a heavily modified system called SentencePiece for models like Gemini. Because they use entirely different dictionaries, the exact same sentence will look like a completely different sequence of numbers to ChatGPT than it does to Claude or Gemini. They literally speak different subword dialects. A chunk that takes one token in GPT-4 might take 3 tokens in another model, fundamentally changing how each AI interprets the rhythm of your prompt. As AI architectures evolve, these dictionaries are getting dramatically larger. Older, early generation models like GPT-2 had a vocabulary of about 50,000 tokens. But modern powerhouses like Meta's Llama 3 or OpenAI's GPT-4 boast massive vocabularies of over 100,000 or even up to 200,000 unique tokens. Why does this matter? A bigger vocabulary means the AI can pack much more complex, longer words into single, solitary tokens. This allows the AI to read faster, pack more information into its context window, and hold much longer conversations in a single breath before it starts forgetting what you said at the beginning. It makes the model tangibly smarter and much cheaper to run per word. However, subwords have a massive, glaring flaw: they destroy numbers. Imagine you want to add 3, 1, and 42. A human intuitively lines up the digits into neatly organized columns. But a BPE tokenizer might see 381 as a single token, or unpredictably split it into 3 and 81. The AI doesn't see individual digits, it sees abstract chunks of text. It's like asking you to perform long division where the number 381 is completely replaced by the concept of the color blue. This bizarre, inconsistent chunking ruins the arithmetic alignment. It makes math incredibly difficult for AI, which is why models often struggle with complex addition unless they are specially trained to break numbers apart into individual digits beforehand. And this brings us right back to our original mystery: strawberry. Why can't ChatGPT count the R's? Because the word strawberry is tokenized into abstract chunks, perhaps straw and berry. The AI is fed 2 unique ID numbers representing those chunks. The raw letters S, T, R, A were stripped away before the AI even begins to think. It never actually sees the spelling. Asking it to count the R's is like showing you a blended fruit smoothie and asking you exactly how many seeds went into the blender. The structural data is already destroyed. The AI guesses, hallucinates, and fails simply because it is physically blind to the individual letters inside its own tokens. There is an even darker consequence to subword tokens, widely known as the multilingual tax. Because BPE tokenizers are trained mostly on English data, the algorithm is heavily biased. An English word like beautiful perfectly matches an existing token and costs just 1 unit of memory. But a Hindi, Arabic, or Burmese word of the exact same meaning might be entirely foreign to the dictionary, causing it to be shattered into 10 or 15 fragmented character tokens. This means non-English languages consume the AI's context limit up to 10 times faster. Worse, since API platforms charge by the token, a user prompting in Hindi might pay significantly more money than a user prompting in English just to say the same thing. So, how do we fix this fundamentally flawed system? Advanced researchers are currently building native Byte-Level Models. Instead of relying on rigid, pre-calculated token chunks, these radical new architectures read raw binary bytes directly from the computer's memory. By feeding the AI the pure streams of ones and zeros that make up the text, we eliminate the spelling blindness entirely. We fix the math misalignment, and we completely erase the unfair multilingual tax. Reading raw bytes is mathematically harder for the AI to learn initially, but it represents the next giant leap in artificial intelligence, promising models that truly understand the deep structure of everything they read. Soon, the entire concept of a subword dictionary might be considered a relic of the past. Let's quickly recap. AI does not read English words, it reads mathematical tokens. We realized characters were too slow, and whole words required an impossibly huge dictionary. So, we settled on subword chunks using the BPE algorithm, like slicing words into common syllables. It's an incredibly clever statistical hack that makes modern large language models lightning fast and highly articulate. But this compromise comes with severe blind spots. It breaks the AI's ability to spell correctly, ruins mathematical alignment for basic arithmetic, and heavily penalizes foreign languages with unfair processing costs. Understanding tokenization is the ultimate key to understanding how your AI perceives the world. It demystifies the magic and reveals the mechanical reality beneath the chatbot's interface. So, the next time you catch ChatGPT's making an utterly silly mistake like hallucinating the spelling of a simple word, struggling to count the letters in strawberry, or failing to align digits in a basic addition problem, don't just assume the neural network is incredibly stupid. Remember the invisible lens sitting between your prompt and the AI's deep neural brain. The model is doing the absolute best it can, trying to interpret our complex human world through the blurry, chunked-up lens of tokenization. It's not a failure of reasoning, it's just the mechanical language barrier between humans and machines. Thanks for watching, and keep exploring the hidden mechanics of AI.